Hochstetter. Phaedra Upton is the geodynamics team leader here at GNS, where she's worked for the last 11 years. She's published widely on oblique collisional plate boundaries, including the Southern Alps, and most recently, tectonic geomorphology has become her main focus, and she'll share some of her work with us today. Here's Phaedra.
Thanks, Katie. E ngā rangatira mā, ki te mihi atu ki a katoa, ko Phaedra Upton tonga ingoa, no o te poti tauamutu me te waihora ahau, tēnā koutou katoa. So thanks for coming along to my Hochstetter. First, I just want to acknowledge that this is work from, pretty much over my whole geological career and work with a lot of other people, some of who I've acknowledged down the bottom there. So particularly Peter Coons and Sam Roy, who are colleagues from the University of Maine. And fingers crossed we're going to submit this paper this afternoon. Dave Craw from Otago I've worked with forever. Nick's also from the University of Maine, then Rupert and Jamie, who ex-GNS, now Vic, and lots of people here, but particularly geodynamics, landslides, and the paleoseismology team. Okay. Right, so the Hochstetter. So the Hochstetter lecture is, as Katie said, awarded by the Geoscience Society of New Zealand. It was named after Ferdinand von Hochstetter, who was an Austrian geologist who came out and did some mapping in New Zealand when that's pretty much what you had to look like to be a geologist or a naturalist. And we see his name around New Zealand in quite a few places. But I also want to acknowledge all the, people that I've worked with and who have taught me or I've taught or inspired me. So yeah, just a much more diverse range of geologists these days, which I think is great. Somebody's not muted. So my talk today is, tectonic geomorphology, and it's aimed at a broad audience. So I'm going to set it up with a series of sort of slides that I've called foundation slides. And so this is the first one. So I just want to talk about the timeframes that I'm really talking about. And often when we think about tectonics, particularly also surface processes, we have, the long-term results of tectonics, so mountain ranges or subduction trenches or the Grand Canyon, which represents millions, almost billion years of geological processes, millennial climate change, glacial, interglacial. And then, of course, there's the short term. So, earthquakes that happen in seconds to minutes, or storms. That's a storm from the West Coast a few years ago. But I'm kind of looking in between these two largely. Failure. Right. Medium term. So I sort of medium term timeframes, and what I mean by that is thousands of years type thing. So multiple earthquake cycles producing valleys and ridges, or river valleys, ranges, that the results of multiple storms leading to incision of a valley or to river capture. So so these timeframes, I just think of them as medium term between the really long term tectonics versus the instantaneous short term. And I'm going to talk about lots of different drivers and processes. And so conclusion right here is that these are pretty much all interconnected. So we're going to talk about surface processes and tectonic processes, and I'll show you that they're interconnected, but they also relate to, say, the material properties, what rocks are being acted on is really important, the stresses, so the tectonic stresses or the topographic stresses. So they're all interconnected. So I've tried to illustrate here, but often the way to really figure that out and look at the processes is to actually pull them apart. And so I'm going to show you an example of how stress and material properties interact, or how stress and surface processes interact, and then through a series of examples that kind of get more and more complicated, bring them all together to show you some examples where all of those interactions, we can see them in the models. So a lot of what I've done has been informed by particularly the Southern Alps, South Island of New Zealand, also the Himalaya and Taiwan and other active regions. But so if we really want to understand the interactions between the tectonics and surface processes, we have to look at both of those. And so, for example, if we think about the South Island, the tectonics of the South Island, we know it's a continental collision. It's a oblique continental collision, so that defines the type of stress state we're gonna see. We have uplift creating topography in the Southern Alps, the Otago Ranges, also in Marlborough. And we're really interested in the faulting, and the faulting was related to the material properties, weakens the rock, as we'll talk about. And what's happening on the surface, so the surface of the Southern Alps is really dominated by the fact that we've got this mountain range in the middle of the westerly, so we end up with a really strong orographic climate. Orographic rainfall produces the rivers and the glaciers in the higher regions, and basically the combination of all of those gives us the landscape that we see. So it gives us what the Southern Alps looks like, or the South Island, and that's what we're going to explore through the talk, how the drivers from tectonics and from the surface processes combine to give us that landscape. I'm going to talk about two different sorts of topography, so I just want to outline them there and explain what I mean. So one is erosional and one is constructional, and I've illustrated them both here using the Wellington Fault. So on the left we have the Wellington Fault and the Tectonic Valley just to the north of us here, and the topography or the relief that we see in that valley is largely erosional. So the river is incising down, it's using the fault, as we'll see, because it's much easier, and so the distance from the valleys to the ridges, from the ridges to the valleys, is largely because of the removal of material, and that's what I call erosional topography. Versus what we've got here in the Hutt Valley in Wellington. Again, we're on the Wellington Fault, but in this case, a lot of the topography and the relief that we see is because of relative movement along the fault. So we're sitting on the downthrown side, the Western Hills on the upthrown side, and so that topography, the relief that's sitting along the fault, while there is a component of erosion, is largely constructional. And of course, many of the landscapes that we see are both. In this talk, we're going to look at erosional a bit more than constructional, but it's got to keep those two ideas in our minds. And then stress. So rocks are all subject to stress, and I've tried to just illustrate it quite simply here, but basically rock, it can be, gravity and tectonic confining stresses. The topography, as we'll see, inflicts stresses on the rock, and also the surface processes do too. And we'll go through several of those during the talk. But simply for the first set of some of the early models I'll show you, so the stress state, it determines the type of faulting that we see. And the type of faulting is important because we're going to look at the impact of that on the erosional processes. So if we have a stress state that's basically extensional, we get normal faulting, and given certain, if it's simple, there's no topography, and we kind of know the rock type, we can predict the angle at which that normal fault will be. So it'll be sort of steepish normal fault versus a thrust fault where you've got compressional material, and we can again predict that the thrust fault will have an angle of about 30 plus or minus degrees, depending exactly on the material. Strike slip faults, on the other hand, tend to be vertical or near vertical. So initially, we're just going to impose these type of faulting patterns on our models, and later on, we'll actually develop them in the models. And material properties. And so, as I said, the rock that is being deformed and or eroded is important. So I've just got a couple of models to show you how the material properties, why they're important, and how different materials respond differently to the same sort of stresses. So here I've got two analog models. One's a phone book, one's a piece of polystyrene foam, and in both cases we're compressing them. So we're putting a compressive stress on them, and they're both producing a fold. The phone book is a series of pages, and it produces a fold by those pages sliding relative to each other. And that's kind of an analog model for this rock down the bottom, which is from the Southern Alps, where we've got sandstones and shale layers. The shale layers are much weaker than the sandstone layers, and so when it's folded, it deforms along those sandstone layers. The polystyrene, or the massive sandstone here, which it's an analog for, you compress it, it folds, and it's folding elastically, and then snap, it breaks. And it kind of breaks along the boundary between the little balls. So we see that we've put the same stresses on these materials, but the response is very different, and it's a function of the material properties. And because I'm talking about surface processes, it's the cohesion and friction angle and the tensile strength that is really important to what we're looking at in this talk. So when I'm talking about stress, I'll often talk about cohesion, maybe sometimes friction angle, or tensile strength. So the tensile strength is the resistance of the rock to being pulled apart in tension. Friction is the resistance of the grains to sliding against each other, and the cohesion is the other component that's holding the grains together. And so this cliff we see from Svalbard, where up the top, where the grains are stuck together, we have the strength and the slope. They're both a function of the cohesive strength and the friction angle of the material. As it erodes, we end up with these talus slopes. The strength and the slope are reduced, and they're now a function of just the friction angle, because that cohesive component has disappeared. So these are the materials with material properties that we're thinking about is the friction, cohesion, tensile strength. So first I want to show you this example of it's an interplay between stress and material properties, and I gave a shorter version of this talk at EGU a year or so ago, and this was in the same session, and it was just a perfect example of the sort of stuff I was thinking about. So I use it as an example of how the stress and the material properties interplay to produce a landscape. And so they were looking at the evolution of these natural rock arches these ones are from Arches National Park in Utah. And they did it with an analog model. They got this sandstone, which was an quarry sandstone, which is weakly cohesive, and they produced arches. And they were able to produce arches by creating a couple of discontinuities here. So this vertical discontinuity kind of separated the block they're interested away from the confining pressure of the rest of the cliff. And then this horizontal discontinuity produced a stress, the idea is it produces stress shadows. And so these in the natural world would be joints of some sort. And what happens is that this rock, its strength is a function of the stress. Its strength, when it's compressed, it's stronger than when it's not compressed. And by creating these cuts, these discontinuities, you create these stress shadows. And then they rained on it with a watering can. And what happened was where the stress shadow is, we get it erodes because it's weaker, and that compressive zone stays strong, and you end up creating an arch purely because of that material property, that it's stronger in compression. And as the arch becomes more and more developed, and actually the compressive stresses increase, so it becomes more and more delicate and more vulnerable looking, but actually it's stronger. And it's purely a function of the erosion is stress controlled because the material strength is a function of the stress. So for the rest of the talk, I'm not going to use analog models. I'm going to use landscape evolution model, numerical models. And landscape evolution models are just physically based numerical models that allow us to simulate terrain changing over time. And there's lots of different types of models, lots of different processes. You can look at fluvial erosion, glacial erosion. You can look at sediment transport, deposition. Mostly we're just looking at erosion. And what we've been doing over years is to add a tectonic component to these landscape evolution models. So instead of just really taking a quite uniform base, or really not thinking about the faults or the tectonics and the particular stresses, we've added those into the model. So we're thinking about the orientation of weak zones, inclusion of the tectonic and topographic stresses, and then the ultimate goal is to really think about the feedbacks between the tectonics and the surface processes. Okay, final foundations slide is just to emphasize that really where lots of what I'm going to talk about, one of the really strong links between the tectonics and the erosion is the link between deformation and erodibility. And basically, as you go from bedrock to a fault zone, you deform the rock and the near surface, you reduce the friction, you reduce the cohesion and the tensile strength. And so in doing so, it's a measure that deformation, it weakens the rock and it weakens the rock tectonically, so the deformation gets more focused into that, but it also makes that rock much more erodible. So we go from bedrock. So a lot of our samples have come from Sam's work. He did his PhD here, and he did a lot of field work and measurements on greywacke, so intact greywacke, but something like granite would be up here, high cohesion, high friction, low erodibility, and as it is deformed, so from greywacke, jointed, cataclysite, right down to fault gouge, then we end up in low cohesion, high erodibility. So there's this, yeah. So we then say there's a link between deformation and erodibility. But in the field, we measure the cohesion because that's much easier than to measure the erodibility. So we're now going to use a series of models to explore the components of this tectonic and surface interaction. And they get more complicated as we go. So first, we'll just look at some simple dipping zones and their interaction for different tectonic models. We will have a quick look at the mobile fault system, so look at these ideas in the real world, talk a bit about topographic stresses and what they are, and then we're going to put it all together using the Himalaya, and then right at the end I'll bring it back and we'll look at the Manawatu Gorge briefly. So here's a couple of quite simple, these are landscape evolution models, and so it's using a model called Child. And I should say that all of these models were largely run by Sam when he was doing his PhD. So he can be credited with these models. So this is a very simple model. Here we're looking down on it. This is a cross section. We've got two faults. One is vertical and one is dipping fault at 30 degrees. The red is the highest erodibility. It's the weakest material. And as we go out this way, we go into the strong bedrock. And it's being uplifted slowly at about a metre a year, and it's a millimetre a year, and it's been rained on at about a metre a year. And this boundary here is the outlet boundary. So that's where the water wants to go. And this makes intuitive sense that the weaker rock erodes more rapidly, so that we end up cutting down through this weak vertical zone, and it's basically controlled by the base level. It'll cut down as fast as it can as it uplifts, it cuts down. The dipping structure, on the other hand, it cuts back much more slowly and cuts down much more slowly. I'll just run the model. You can just see that in action. And this is because it can cut down this weak zone to here, but then once it's cut down through that weak zone, it either has to cut through it or more likely erode this stronger material. So the rate of incision of this weak zone is still actually controlled by the strength of the strong material, versus this one where it can just cut straight down and it's controlled by the base level. This has been run a bit further, but you see the same thing. And there's a really nice example of this in the South Island in Central Otago in Thompson's Gorge in the Rise and Shine shear zone. So this is a photo of there's a nice road cutting through this gorge, and we have a dip slope down here of the Rise and Shine shear zone, and then a much steeper slope. And so here's a cross section. There's the fault zone, the dip slope, and steeper slope. And so the stream is cutting down this fault zone, but it gets to cut further down. It requires actually landsliding of this intact rock. And there's just a couple of movies. So one shows the elevation evolution as that stream moves down the dip slope, and this one just shows the stream power as it's moving along. So quite simple and intuitive. But you really get fault zones or weak zones just one. So let's look at the interaction of different fault zones for different tectonic models. So we've taken these idealized fault orientations. So a simple convergent thrust zone where we'd expect the fault planes to be at about 30 degrees. Simple strike slip faulting where we'd expect them to be vertical, and then in between, so an oblique system, which is largely what we've got here in this. Got in the South Island, where the fault planes are rotated. They're steeper than the pure convergent example, and because they're rotated, they end up crossing each other at the surface, whereas in this case they're just parallel. So these are our three examples. These again are similar models to what we saw before, just with more weak zones. So again, we're looking straight down. We're looking at map view straight down on the models. This is the strength pattern. So here we have these 30-degree dipping structures that are all parallel. This is the strike slip system where we've just got one fault. So it's similar to what we saw previously, where that one vertical structure dominates, and then bedrock erosion around it. And in this case, we have oblique systems, so that they're rotated, they're steeper, but they also cross-cut each other. And again, the outlet is down the bottom of the slide. So here we see the main rivers cutting along those fault structures, and then at some point they cut down. They have to cut through the bedrock, and then they meet the next lot of structures, and they have to cut down through the bedrock to get here. This is really quite similar to what you see in Taiwan, where you've got a series of thrusts that are parallel thrusts, and so you see these big wide open river valleys along those thrust faults, and then the slope and the main mountains are orthogonal to that, and so we end up with these big wide river valleys parallel to the faults, and then these really steep bedrock reaches which connect them, similar to that. In this case, because the weak structures intersect, the rivers can really take advantage of them much more, and so we'd expect this landscape to incise more quickly than this landscape, because it can take advantage of those, and it doesn't really have to erode the bedrock so much. So let's take some of these ideas to the Marlborough fault system and look at what's happening in a real system. So Marlborough fault system is this area here, Northern South Island. The Kaikolda earthquake ruptures were in this region here, but we're really going to look at these big valleys that cut through. So there's the Hope fault here, Clarence, and the Awatri, and this is a photo of the upper Awatri. And so the system is really dominated by these this area is dominated by these two big rivers, the Clarence and the Awatri. And what we're seeing here is really actually quite a combination of that erosional and constructional type of topography that we saw. So the faults are in red, the Awatri fault and Clarence fault. And so for this area, the two main rivers follow those faults, but they're now incising away from them. And so it's a combination of the block control, but also there's erosion control. And then the Clarence, the Clarence starts way over here in Lake Tennyson. It flows north to south, cuts across, and then there's these north-south tributaries in this region, And then it isn't really to this region, this area here, that it starts to follow the northeast, southwest sort of angle of the faults, and similar to the Arbitrary here. And probably a lot of these rivers actually used to flow down the Arbitrary, and they've since been captured. But if we look at the orientations of the faults and the rivers in these two regions, this is work I've done with Alison Duval. So Alison and her students did this work largely, and they analysed the inactive and active fault trends in in this, what she's calling the Western Block and the Eastern Block. And we see that in the Eastern Block, here, that the faults are all sort of northeast, whether they're inactive or active. But to the west, there's really quite a strong difference between the two. So the active faults, and active is based on the active fault database. So I'm sure there can be some debate about active versus inactive, but largely the active faults do follow that northeast type orientation, whereas the inactive ones, or the less, are more northeast. But when we look at the river systems in the east follow the faults, except for these ones, which are largely having to get out to the sea, so they swing around to get out to the sea. But in the west, the river systems are much more aligned with the inactive faults than the active faults, and that's why we see that complicated system for the Clarence. So, and I think what's happening here is that these faults are reflecting the previous tectonic regime. What we're seeing in these northeast structures over here are more Southern Alps type structures versus the real Marlborough Fault type structures. And as the plate boundary is shifting, we're getting one tectonic regime, which is what we think of as the Marlborough Faults, and the current tectonic regime is overprinting this older, less active regime. But it's quite a recent thing, and so the rivers are actually still really using those older structures. So they might not be active anymore, but they're still weak. They're still weak zones, and so it reflects that strength, material strength change from the faulting. And it also, I think, reflects that once a river is entrenched, it actually takes quite a bit to change the orientation or to capture it. But we do see lots of captures happening. We do see where so the Clarence is starting to capture, and has captured things that used to flow down the Arbitrary. There's places in Lewis Pass where you can actually see, like Henry Saddle, and that you can actually see where the river is flowing one way, but another one is eroding down one of these active faults, and you can see where in 1,000 or 10,000 years, or when there's a huge storm, where it will actually capture, and so we'll end up with a change in the river orientations. Right, so topographic stresses, what are they? So I'm just going to talk a bit about what topographic stresses are. So on those previous tectonic models, we assumed that the surface was flat, and that's so those idealized thrust folding 30 degrees, sigma 3 vertical, that assumes a flat surface. But of course, in active mountain belts, which is really what we're thinking about, we have a lot of topography, and so we end up with in the near surface, the stresses are rotated by the topography and impacted by the topography, and in several ways. So one is where you've got a big mountain, you've got an increased normal stress, so we increase, it strengthens beneath a load. If we end up with a big hole, so a big river, that weakens it, and we get quite significant shear stresses that are associated with slopes. So I've just taken this photo of Falling Mountain in Arthur's Pass. It's a earthquake-induced landslide here from 1928 earthquake, and I'm going to split it and use this to try and illustrate those different stresses. So blue is a compressive stress, red are extensional stresses, and green are shear stresses. So if we to start here, and if we think so we've got the mountain and the valley here, And if we look at the normal stress at just below the valley, at the level just below the valley, we can see that the normal stress beneath this valley is considerably less than beneath here, because there's a much bigger load on that. We also get compressive stresses at the bases of the valleys, so that's increasing the compressive stress there. And then we get extensional stresses, so near the ridges. So if you tramp a lot, you see those ridge rents or sapelins, so that's reflecting this type of stresses. It's probably where this big landslide was initiated up here, and then along the slopes we get an increase in shear stress. And if you increase the shear stress, that actually can bring the material closer to failure, because you're increasing the stresses that are so a steep slope is more prone to failure than a flat one, because of the increase in the shear stresses. So now I'm going to try and put all of those together into so we can look at the material properties and the stresses and the tectonic boundary conditions and the surface processes, and see how they are reflected in the landscape, and see just how interconnected they all are, particularly in these active collisional zones. And to do this, we're going to go to a tectonic corner. We're going to go to the Namche Bawa tectonic corner on the eastern Himalaya here. And tectonic corners, they're kind of the type example of tectonic landscape evolution. They're where some of the really early work was done, but they're just really useful because the tectonic regime changes. So we end up with convergence, changing to strike slip and an oblique system. So we can kind of see it all happening in these regions. It's also dramatic topographic gradients. So those topographic stresses that I just talked about are really make a difference in these regions. So, we're looking at 7,000-8,000 meter peaks with gorges that are only a couple of thousand meters. So really steep gradients, steep slopes, and they tend to have dramatic surface processes. So in this case, really high monsoonal rainfall in southeast Alaska, lots of snow, and high energy rivers or glaciers. So it's kind of all happening in these regions. So as I said, we're gonna go to this corner here where India is colliding into Eurasia, and we're going to use a very, very simplified tectonic model, which so it ignores a lot of the complexity, but it does capture the basics. So unlike all the previous models I've shown you, we've got a geodynamic model, and then we're going to have the surface process model sitting on top of it. And so the geodynamic model, we have this block which represents India is pushing into this block which stays still, and it represents Eurasia. We model down to 50 kilometers, but we're really focused on the surface of the crust, and we impose the monsoonal wind direction. So there's the geodynamic model to model the stresses and where the faults develop. There's the orographic atmospheric model, and then there's the surface process model in the middle. And they're all, and so as the mountains build, the orographic model changes the weather patterns and drives the surface process model. And I'm going to show you two models basically, and there's just one difference between the two models. In this first series, the faults develop, but the model doesn't know that they're more erosive. So there's no link to make it more erodible. So the surface process is just seeing a uniform material. And that's not realistic, but it's illustrative. And so this is the geometry, and this is through time. We're uplifting these ranges, and we're developing faults, and we're developing thrust faults along there and then along here, and a big strike slip fault along the edge. But the surface processes only really sees the topography. So we build these mountains, and we build rivers on top of them. And this is the river system that's developed from that model. And basically the drainage from the mountains, it's perpendicular to the range, and it's slope controlled. If we then put in a strong cohesion erodibility link, so we tell the material that it's not only is it weaker for the tectonics, but it's easily erodible, and everything else is exactly the same, we end up with a really strong river system along the faults that develop. So, and also, yeah, so we end up with a drainage that's quite different, because it's, in this case, it has this range parallel component, and it's controlled by the material properties. In the previous example, it was controlled by the slope. It was controlled by the fact that the water was running down the hill. But now it's controlled by the fact that we have these weak zones. So so I'll just run these two models that they're just movies of the same thing. So they just, so we see the range developing, another range developing, and the rivers cutting through that. And yeah, so I'll just run that again. So we develop a range. We've got a fault in here, but it's not seeing that it's erodible. Another range pops up, but there's enough, because the rain is coming from this side, there's enough energy in that system just to keep cutting down. So as it comes up, it just keeps cutting down. Versus this one, where we see where this is weak, and so we get the faults developing in here, and we actually, and here we can see a river that's cutting right through, and then it gets blocked off by that uplift, and it's easier for the water to go down that way. So here the rivers are controlled by slope and the amount of water that's coming off the slopes. And here these long rivers are controlled by erosion of the fault weakened rock, and the short tributaries are still controlled by slope. So when I gave this in Dunedin, Dave, Craw and Simon and a few others said to me, it's too much erosion, too much erosion. So I've added another model quickly, just another couple of movies, which are the same geometry, except in this case, instead of, so we know the monsoon is driven from the south, but what happens if you flip it around and drive it from the north? So, so in this example, the wind is from the north rather than the south. And again, we've got no link, no cohesion link, and then we've got a cohesion link. And because all the water's coming, the rain is coming from the north, we get quite a different pattern. And in fact, we get a pattern that's really dominated by uplift and is really constructional, because there's not enough water to drive rivers to cut through these ranges. And actually, even when we put the strong linkage between cohesion and erosion, we do get these valleys forming in here, but it's not as dominant. So it's not as dominant, so in this case, it's really controlled by where the rain is coming from. The rain is coming from over here, and we're getting this rain shadow, and so that's what controls it. So as I said, everything is quite interlinked, and this would be more like, say, Central Otago, because of the rain shadow. And so in Central Otago, we have faults, but we get ranges. Oh, I think there should be another picture there. Yeah, so the orogenic drainage network that we see, whether it's in the Himalayas or in say, the South Island, it tells us a lot. It is a first order representation of these feedbacks, but it's the tectonics. So what's driving the tectonics? It's the long-term climate trends, where the rain comes from. So our wet west coast, our our monsoon that's driven from the south, and the fluvial glacial erosion. And I should have added, and actually the material properties, I should have added that too. And so we can start to look at these landscapes, and using our knowledge of tectonics and everything else, we can start to look at landscapes and make predictions about what's driving them. Or I mean, for modern settings, we obviously know what the tectonic setting is, but for ancient settings, we can maybe look at landscapes and then use those to give us some idea of what the tectonics might have been. So just to finish off, I'm going to come back local and talk about the Manawatu Gorge, because I think we can see some of these processes happening in the Manawatu Gorge. So there's the Manawatu Gorge between the Ruahine Ranges and the Tararua Ranges there, and at the moment all of this area drains through the gorge and out here. But the genetic data from fish, mostly from fish I think, suggests that about 700,000 years ago, that gorge wasn't there, and that this basin was connected right through down into the Ramunahanga down here, so that the Manawatu flowed down here and not through there. And so that something happened to cause the river to be captured. And this is just the genetic data, which suggests that that these catchments and these catchments in the southern North Island were connected somewhere post about 500,000 years ago. And about 1 million years ago, all of these southern North Island, northern South Island were connected according to the genetics. So here's the Manawatu Gorge here, and in this case, I think it's the tectonic control is that we have a lot of uplift of the Tararuas here, we have a lot of uplift of the Ruahines here, and so this was a low point, and so, you know, 1 million or 500,000 years ago, this was a low point. There was a wee bit of something stopping it flowing, whereas now it's still a low point, but there's very dramatic relief. Oh, my slide. Okay, so yeah, so there's dramatic relief. So actually, I've done some modelling to show that the shear stresses. So this is just an elevation model and calculating the topographic stresses, and that the shear stresses in that gorge are really quite high, and actually for strength parameters based on tallest values from Wellington suggest what we see from the fact that there's a huge landslide down the gorge, that the slopes in the Manawatu Gorge are really, really close to failure, just from the topographic driving forces, without any tectonics or anything, just that the stresses the slopes are so steep that it means that they are close to failure. So the genetics suggests that this was coming through here, and what probably happened was that Mount Bruce here, that when Mount Bruce started to uplift, so that this region started to uplift, that was enough to stop this flow and to put a drainage divide in this region, which sent that river backwards, and then enough so that it flowed through the incipient Manawatu Gorge, and as stuff is uplifted around it, it's been able to keep cutting through. So there's been enough flow to cut through, and also since it keeps cutting through and we create those steep slopes, the shear stresses on those steep slopes, it's a feedback loop, because it makes that material, it's easy to fail, and it can continue. So it can continue cutting through here even as the material is uplifting. So hopefully I've illustrated some of the thinking of really how we can pull together our knowledge of the tectonics, our knowledge of surface processes, and the things that link them. So the material strength is really the important one, and that we can see the impact of strain weakening of faulting in the landscape because of that cohesion or tensile erodibility link, but also that the landscapes you create and the stresses that you create in the near surface also feed back. So we end up with sort of several feedback loops. And then of course there's the larger scale feedback loop of producing big mountains and producing orographic rain. And they all link together to shape our landscape. Thanks.